Hi everyone. In this video, I want to go over an online homework problem that I came across. It is calculating a boiling point from standard thermodynamic values. Now, the thing is, it's a short problem, and a lot of times it's the short problems that give students difficulty because there's not a lot of information to go on. Right now, this problem is not screaming, use this equation or use that equation. It's asking for the boiling point. It's asking for a temperature boiling point for BR2. Now I see delta H and I see entropy. Thinking about all the reactions that use enthalpy and entropy, we could use delta G. It's in standard states or standard conditions, so we'll call it delta G naught equals delta H minus T delta S. So I'm good with using this to get the delta H. I'm good with using these values to get delta S. The issue is, what is T and what's delta G, and how do I relate it to the boiling point? I think what we need to do is we need to get a chemical reaction, because right now I'm kind of lost. I thought this delta G is supposed to be for some type of reaction, and it is. Think about the boiling of Br2. You start with Br2 liquid, and you have a change. You have a process that goes to Br2 gas. So there's your chemical reaction. And yeah, now we do have delta H's associated with this process. We have delta S's associated with this process. And we have delta G's associated with this process. But what is the boiling point? Think about it this way. Go back to your heat curves. When you have a heating curve and you heat up the liquid, you add heat until you get to a temperature that equals the boiling point. So here you have liquid. And do you remember what happens at the boiling point as you add heat to a liquid? It plateaus. It plateaus. That's the transition. And then once you get all of that liquid to be a gas, then you start heating up the gas and the temperature starts rising again. So, whoops. The y-axis is temperature, and this is Q added, heat added. We want this temperature right here. We are at this transition point, and we didn't emphasize it when we talked about heat curves, but that transition, the liquid and the gas are at equilibrium. That's a huge point. The liquid and gas are at equilibrium. It is neither spontaneous nor non-spontaneous at this temperature for the liquid to turn into gas or the gas to turn into liquid. You have equal probability of doing either way. What does that mean? We are at the border of spontaneity. This temperature for these two phases, it is neither spontaneous nor non-spontaneous in either direction. That means delta G equals 0. That's the key point right here, or the exclamation point. At the boiling point, delta G for this reaction is 0. And there you have it. We're going to set this to 0 and then solve for T. Okay, but do you see there are two main points you got to realize in this problem. The first one is give yourself a chemical reaction that you can focus on. Understand that when these two are in equilibrium, delta G is equal to 0. Okay, and then obviously you'll need to know the equation, where to plug in the numbers. Okay, now just be careful. You know, delta H is in kilojoules per mole. entropy is in joules per mole dot K. And again, remember, we're solving for T. So why don't we figure out delta H first? Products minus reactants. Products minus reactants. So the delta H for this reaction, these are formations, but that we knew that. You get the delta H from the delta H of formations of each component. So if you really want to put the equation, it's this one. Delta H of formation of the products minus summation delta H of formation of the reactants. So the product is the Br2 gas. So that goes first, 30.9 minus 0. Oh, Br in its bromine in its standard state is diatomic and liquid. When your element is in its standard state, then your delta H of formation is set to 0. So there's 0.0 down here. And we get, for delta H of the reaction, that's 0, 30.9 kilojoules per mole. Okay, that will go for delta H. Delta S. Delta S at standard state equals, now take a look, it's a little bit different. It's still the summation. We have coefficients of 1, so we don't really have an N. But I'm not going to put delta S. It's the entropy of the products, summation, minus the summation of the entropy of all the reactants. But again, we only have one product and one reactant. So you take this number first, 245.5. But right now, I'm going to change this to kilojoules. So it's 0.245, 5 kilojoules per mole dot K. And this one is 0.152, I keep doing that, 2 kilojoules per mole dot K. Products minus reactants. All right, let me do that down here. We have, it'll be interesting, we want to know, delta H already we can see is endothermic, but that makes sense because we are adding heat, adding enthalpy to make it from liquid to gas. We expect entropy to be what? When you go from liquid to gas with the same number of moles, the gas has more chaos, more disorder, so we expect delta S to be positive. The entropy of the bromine gas is 0.2455 minus the entropy of the reactant, which is the bromine liquid, 0.1522, and I get a calculator. 0.2455 minus 0.1522. Double check your numbers. Yep, that looks good. That's 0.0933 kilojoules per mole dot K. Okay. Let me try to fit everything onto one page. So now we're going to substitute it into this equation. I like to plug in the numbers, then rearrange. So we have 0 for the delta G equals, delta H is 30.9 kilojoules per mole, minus T, delta S is 0.0933. Let's take, we could bring this over to the other side, so that's negative 30.9 divided by negative 0.0933. So without recopying a lot of numbers, we can do this all on the calculator. 30, whoops. So we bring this over to the other side. So it's actually negative 30.9 divided by the negative of this value here, negative 0.0933. The T should be positive, right? In the Kelvin scale, temperature is always positive. Okay, so here we have 331.2 Kelvin equals T, and then let's go ahead and convert this to Celsius, 273.15, and we get 58.0 degrees C equals the boiling point. Okay, again, just don't panic when you see something very short like this. Try to get an equation down, okay? Try to get a chemical reaction written out. And then, yeah, the jump is to realize that the temperature when it's at boiling point, these two are at equilibrium, meaning that neither direction is spontaneous. So the last thing I want to put here, just as a reminder, at the boiling point, neither direction, either forward or reverse, is spontaneous. Neither direction is spontaneous. They are at equilibrium, which means that delta G equals 0. So there's, I guess, the main key to solving this problem. Final answer, 58 degrees Celsius.